So when we study reaction rates, we can say the change in concentration of a reactant or product per unit time. Okay? So when we talk about rates of a reaction, we're concerned about the concentration. And remember, concentration is moles per liter. So the reaction rates we're looking at is a change in moles. I've written a reaction here, A plus 2B giving us C plus 2D. As A and B combine to form products C and D, the concentrations of what's over here on the left, or the reactants, are going to decrease. So A and B are reactants. So their concentration will decrease. Okay, C and D are products, and their concentration will increase. So as this reaction proceeds, we're losing A and B and gaining C and D, and the concentrations are going to change accordingly. So if we wanted to write the rate of the reaction in terms of A is going to disappear, so we're going to use a negative change in the concentration of A per change in time. Where if we look over on the product side, we can write the rate as positive change in concentration of C per change in time, because C is going to have a greater concentration as this reaction progresses. So the stoichiometry of a chemical reaction can tell us a little bit. And what the stoichiometry tells us is that the rate of disappearance of B is going to equal 2 times the rate of disappearance of A. Okay, and this is because when a reaction happens, we need 2 moles of B for every 1 mole of A that react together. Okay, we can also say that the rate of appearance of D is equal to 2 times the rate of appearance of C. And again, this is dictated by the stoichiometry of this particular equation. So we can set up kind of a general rate expression for this particular reaction, and this will work for pretty much any reaction. And we need to take into account the balanced chemical equation and the stoichiometry. So we can write a rate expression as negative change in concentration A over change in time. That's going to equal negative 1/2 the change in concentration of B over the change in time. Okay, because this coefficient of 2 in the balanced chemical equation here is going to correspond to this coefficient down here. This is also going to equal positive change in concentration of C per change in time, which is going to equal positive 1/2 the change in concentration of D per change in time. And again, the coefficient of 2 here in front of the D is going to go down in the denominator of our rate expression. So for any given chemical reaction, we can write a rate expression based on this. And in the next video, we'll take a look at some experimentally determined concentrations, and we'll figure out how we can look at the reaction rates for each of those.